Hello, how have you been? I've been, well, no time has passed for me. So since the last time you saw me, I've saved the last video, and that's fine. All right. I will remind you again, though, I've lost track of what day this is. This might be Wednesday, in which case your problem set's already been due. I'll remind you of this. I am very quickly approaching the end of chapter 4. Please, please, please look through the material that I sent to you that is covered in chapters 5, 6, 7, and tell me about anything you want me to review. I am oh so happy to do so, but I can't do so without your guidance. So I do need to know what you would like to see. The other thing that happened since last time is that I cleaned the board. So there, I hope that's helpful also. All right, so we were looking last time at 3 forms. And I said that they are evaluated on tetrahedra, which are 3-dimensional triangles, if you want. I didn't say that last time, but that's what they are. And we've been doing pullbacks each time, so let's talk about pullbacks. Our standard tetrahedron is much like our standard triangle, except in a higher dimension. Here's our standard tetrahedron. It's a pretty nice thing. It's our standard triangle, but just with a z component included. It's worth keeping track of it. It has 3 side lengths. The perpendicular sides, at least, are all length 1. So the volume of this is 1/6. And that will be important, much like the area of the triangle was important at the end when we did pullbacks in 2 dimensions. This is a positively oriented tetrahedron. You could check that. It's not so hard because the numbers are so simple. So, okay, great. So suppose I want to pull back a generic tetrahedron to our standard tetrahedron. We need a parametrization. Our parametrization should not surprise you at this point, I hope. It now has 3 variables. And if all of our 3 variables are 0, I should go to point A. If I have 1 in the first variable and 0 in the 2 variables, in the next 2 variables, I should go to point B. Of course, this is a little larger than I need it to be. So I have my standard B minus A displacement vector. If I have 1 in the second variable, I should go to C. And if I have 1 in the third variable, I should go to D. All right, so that's fine. So this transformation takes a unit cube to a parallelepiped with some volume. And we can find out what that volume is in one of 2 ways. We have a nice approach here. We can compute the pullback of dx, dy, dz, and then multiply by the change in volume, which is given by just finding the volume of the associated parallelepiped, which we do with our scalar triple product. So we have that way of doing pullbacks. Or if you want, you can use our multiplication rules. I didn't give them a name last time. Sometimes that's called exterior algebra. I think that's just so you can sound smart. I don't think there's really much need for calling it exterior algebra. It's just our way of multiplying differential forms. But we could do that, and we'd end up in the same place if we use this, or if we don't like calling it that, this is del x, because it's in the first component, del u, which is b minus a. So you can use the pullback of the one forms like before. This is del x del v, and this is del x del w. That gives our pullback for our one forms, and then we can multiply them all together with the other one forms and using our exterior algebra, which sounds like something from space or something. I don't know. So that's all well and good. I think I better do an example of this, and we'll see how we choose to do our multiplication. Probably we'll practice doing exterior algebra. That's probably a good idea. All right, so let's do an example of this. Making sure we're on board with how to compute integrals of three forms using pullbacks. That's our goal. So, all right, let's take this away and actually have a concrete example. I'm going to leave you up there. I feel as if I said that last time. I'm not going to make the joke about it. Although I do miss you when you're gone. Anyway, let's let the tetrahedron be 2, 1, -3, 0, 2, 1, 5, -2, 4, -3, 1, 0. And just to make sure that I'm doing the same example from the book, because otherwise I'll get a different answer, and then I won't know why I got the different answer. It would only be because I changed the numbers, which would be dumb. All right. So there's a tetrahedron. There's our standard tetrahedron. We first need a parametrization. We have this written right here. So let's see if we can handle doing this more quickly than usual. It is A plus U times B minus A. So the plus is really minus in this case. B minus A, that's just plus U. B minus A, this is plus 4U. I am actually doing this, which is kind of dangerous to do this arithmetic on the fly, but I am. So we'll see how this works out. Then we have plus V times 5 minus 2. This one becomes minus, and this one becomes 7. And we have D minus A, so this one becomes -5W. And 1 minus 1. Oh, finally something canceled. It seems only fair. 0 minus 3. We have minus -3, so plus 3W. All right. So there's our parameterization. That wasn't awful as far as things go. What we'd like to do next, I'm going to use exterior algebra, and we'll see how that goes. So what I would like to do next is find the pullback of dx, the pullback of dy, and the pullback of dz. Remember, with our one forms, pullbacks are really just taking derivatives. So we take the derivative of each of these lines of our parameterization. We get 2 minus 2 du plus 3 dv minus 5 dw, not 2. Silly person. I do know how to take derivatives of constants. Du minus 3 dv and 4 du plus 7 dv plus 3 dw. Great. And now what I want to know is what the pullback of dx, dy, dz is. And one thing I do know is that we set up our rules so that it's the pullback of dx times the pullback of dy times the pullback of dz. And apparently that is 2 du plus 3 dv minus 5 dw times du minus 3 dv times 4 du plus 7 dv plus 3 dw. And now you think two things in rapid succession. You think, wow, I really don't want to distribute all that. And then you think, oh, wait. This is not going to be so bad because most of the time we get 0. Remember, du is 0. dv is 0. dw is 0. And just in case you were worried, what? Du, dv, du, yeah, that's also 0 because you could switch the order of these, insert a negative, and then you have du next to each other, and that's 0. Or dv, du, dv, yeah, that's also 0. The only time we don't get 0 is when we're multiplying u, v, and w. Okay, great. We just need to make sure the order is right, but we will end up with a du, dv, dw. And you might have said, this is going to be painful. Why would we ever want to do it this way? I don't know about you, but this to me feels a whole lot easier, quite honestly, than computing that scalar triple product did. This to me is easier than cross products. It really is. You might disagree and you have the other way, that's fine. But this seems not so bad. So let's see if we can handle it. Let's start with the 2 du. Don't multiply by du because that's 0. So 2 du, negative 3 dv. Don't multiply by u or v because that's 0. 3 dw. And that is u, v, w. So 2, negative 3, 3. That sounds like negative 18. 2 times negative 3 times 3. Because the scalars come out in front and commute wherever they want. All right, so that's good. What about the next option? If we take dv here, we can then have dv. Don't take dv again, because that's not going to be very interesting. dv, du, we have v and u, and w. All right, so that's dv, du, dw. Notice that one of the pairs is switched, so we'll have to put that in the right order and get an extra minus sign. That's dv, du, and w. That's 3 times 1 times 3, but we have an extra negative sign. So that's negative 9 du, dv, dw. Okay. What's another way? Those are the only ways for these two. So what if we take w for the first one? For w for the first one, we have 2 choices for the second one. We haven't had that before. But okay, we're doing well, so I don't think we should be scared. So let's take du first. W, u, Don't take U again. Don't take W again. V. So negative 5 dW, 1 du, 7 dV. So it's either positive or negative 35. We should check about the order of things here. WUV is the same as UVW because I can switch that W twice. It's negative of du dW dV, and then the same again as UVW. So we switch signs twice. We would have computed negative 35. We keep negative 35. We are feeling awfully negative, which you might think is a bad thing. I want you all to stay negative. Keep doing your testing. I did have a student who was banned from class today. Not rightfully so, but keep doing your testing and stay negative. I want you all to be really negative. All right, let's keep going. So where were we? We did W, U, and V. Yeah, that's how we got 35. Okay, good. We also have an option of W, V, and U. And that looks like a very big number, but I think I can handle it. So W, V, and U. We have a question, do we have positive or negative there? That's interesting. Now we have so many that it's a little tricky to keep track of. WVU is negative dV dW du. I switch the first two. Is positive dV du dW. I switch the last two. Is negative du dV dW. So apparently we will have an extra negative sign out of all of this. We have negative 5, which are we doing? W, V, U. Negative 5, negative 3, positive 4. 4 times 5 is 20, times 3 is 60. I did manage to do that arithmetic. These are negatives. They multiply together to get a positive. So we would have positive 60 except for this, and we did stay negative. Way to go. Let's stay negative all the time. All right, now all I need to do is successfully add these numbers together, which is too hard for me. I'm going to skip adding the numbers together just because I should be able to do that. What? 9 and 35 and 60 we agree with. The book seems to think it's positive 18. They're not staying negative. What good are they? All right, let's see why it should be positive 18. U, V, W, negative 2U. Oh, negative 2U. Those of you being concerned about this all along. And that was the only one that ended up there. Okay, fine. We should have changed the numbers to make that be just so that we could stay negative. Yeah, it was great while it lasted. Anyway, the book says we add up these numbers and get negative 86. And so if we integrate our triangle, our tetrahedron dx, dy, dz, this pulls back to the standard tetrahedron with an extra negative 86 factor, du, dv, dw. Remember, the standard tetrahedron has volume 1/6. That's why it's still written up there. And we get negative 86 over 6. Which the book tells me cleans up to negative 14 1/3. I don't care terribly much about that. All right. Point out, the single point here that I do want to make. This looked scary, but it was not that bad because almost everything was 0. We only ended up with 4 terms we had to be careful about. yes, we did have to be careful about our signs. And I apparently needed to be careful about taking that partial derivative correctly. I think that was when I was failing to differentiate 2 correctly. Someone must have been shouting out a long time ago, hey, hey, hey! And I really wish you were all here to shout at me that way. But oh well. All right, that's our 3 forms. We are next going to do K-forms. We have some generalizing, yes, to do. I'm going to pause for a moment. All right. I don't know why I paused. No good reason. I remember I can bring water here. I should remember to do that, especially if I'm doing the crazy thing of recording 2 days at once. All right, so taking this away, we're now trying to move up to generic dimensions. And the hardest part about this maybe isn't the K-forms, because we're kind of used to what those should be, as long as we've noticed a thing or two. So let's see. But the hardest part is, what are we going to evaluate our K-forms on? Well, we know how to write it. So again, here we go with dimensions. Well, actually not 0 dimensions. We might get there soon. By which I mean, I hope we get there today. So remember, 1 forms, we had 2 points. And they tell us plus or minus the length. This is getting tiresome because we do this so many times. And these were called segments. And for 2 forms, we had 3 points, and these were called triangles. And we get plus or minus the area. And for 3 forms, we have 4 points, and they are called tetrahedra. And we get plus or minus the volume. And so now we're trying to generalize this to K-forms. So how does this generalize? Well, one thing we notice is we have 1 more point than the dimension. I think the best way to account for that is by labeling using 0, because we really have a base point and a bunch of other points. So we have K plus 1 points. This spans something. This thing is called a K-simplex. Simplices are the generalizations of triangles and tetrahedra and line segments for that matter. Okay. And well, so this has to live in at least R1 or more. This has to live in at least R2 or more. This has to live in at least R3 or more. This has to live in at least RK or more. And it should tell us plus or minus the K volume. All right, well, who knows what that is? The volume in that dimension. And it's worth thinking a little bit about what these volumes are. I think this is a fine time for our colors again. So the length of this was B minus A. I don't know quite what those vertical bars are there. I don't mean absolute value. I do mean difference. Well, I'm going to leave them there because I will tell you what I mean by it. Because I do mean something, actually. For triangles, yeah, this is not a good idea. It just makes it hard for you to see. Too much writing in color is not a good thing. Highlighting things in color is okay, but All right. So for triangles, we noticed that we had some determinants. That's one of the many ways we thought of things there. And it's the determinant as long as we're in R2. And by the way, if we're not in R2 and we're just working with dx, dy, then we just take the x and y components and ignore the higher components. It's determinant now. Now you might look at that and go, how can I take a determinant there? There's only two things. But remember, this is a 2 vector. And this is a 2 vector. So it's the determinant of b1 minus a1, b2 minus a2, c1 minus a1, c2 minus a2. Okay. Write that a little better. Make this determinant line go. Okay, we saw that. That's interesting. And I'm going to erase that now. But remember, these are 2 vectors, and this does make sense as a determinant. Oh, that thing up there? Yeah, all right, it's weird. I'm not denying it. That's a determinant of a 1-by-1 matrix. Even those of you who have studied lots of linear algebra, who've taken linear 2, maybe you've never thought about the determinant of a 1-by-1 matrix. It's, by the way, really, really easy, and that's why you never thought about it. A 1-by-1 matrix is just a number. You happen to put some brackets around. But okay, that's not very scary. And the determinant of a 1-by-1 matrix is just that number. All right, well, that's not bad. We should not have been scared by that. Okay, so that's good. So this is, I do actually mean determinant, although it's a little strange to call it that, it is that. All right, so here we have, in our 3-dimensional case, the determinant of b minus a times c minus, not times c, but b minus a vector for the first column, c minus a vector for the second column, and d minus a vector for the third column. And that's times 1/6 for the reasons that we talked about before, that the tetrahedron is 1/6 of the volume of the parallelepiped. And so in general, what's the volume? And oh, by the way, these things are giving us the sign values. So that's nice. Not just the magnitude, but the sign as well. And next we have K volume. How am I doing on time? I have no idea. All right, that's fair. That's fair. So next we have our K volume. Great, great, great. And it then, if we follow the pattern here, well, is apparently a determinant, that seems reasonable, of a1 minus a0. Notice we've shifted so that a0 is playing the role that a just did. So that's the thing we subtract off from everything. A2 minus a0, 3 minus a0, all the way up to a k minus a0. These are assuming that these things are k vectors. So we do actually get a square matrix. Otherwise, computing its determinant is going to be rough, by which I mean not defined, in case you thought I meant something else. And then we have a coefficient out in front. And the coefficient out in front, well, we look at maybe a pattern here, or there is actually a fun exercise in the book that I think I did not assign of working with hypervolumes. And so that's interesting, but showing you that the volume of a K simplex is actually, guessing the pattern here, guessing right, it's 1 over K factorial times the volume of the K-dimensional box. It's not a box. I wonder what's the right name for K-dimensional parallelepiped is? I actually don't know off the top of my head. Well, anyway. Hyperparallelepiped, maybe. All right. And so that is the basic idea that we generalize to when we're dealing with K-forms. I'm going to stop and make sure I proceed correctly at this point before something bad happens. Hold a moment. All right, I checked a couple things. The book now talks about permutations and probably does more harm than good. So let's not do that. If though, this does remind me of something important. If you want to add to our 5, 6, 7 list determinants, because I've been talking a fair amount about determinants, I think they may be even on our 5, 6, 7 list. But in any case, if someone has a problem with determinants, please tell me. Please tell me. And we'll talk about how to compute determinants so that that's not a scary problem. All right. This does inspire a question, though, that seems worth wondering about. We have 1 forms and 2 forms and 3 forms. And we could define 4 forms. Apparently, it's 1/24th of the volume of something like a hypercube, but a parallel hypercube, who knows? That's all fine. What if we go, however, in the opposite direction? What if we go to 0 forms? All right, well, that's weird. But we could try it. We can generalize this stuff backwards. We'd have 1 point, because we always had 1 more than the dimension. And it would live in, all right, R0 or more. The or more part is really important here because R0, I think, is probably just the origin itself, maybe, or it's empty. I don't know if you care about it. But more importantly, it's or more. So it can live anywhere. So a 0 form then takes a point and sends it to a real number because remember, we've always sent to real numbers. So they always have real outputs. And so this, a 0 form, is a fancy way of saying some function from R n, who knows what it is, however many dimensions our vector happens to live in, to just R. And these are just ordinary functions. That's just ordinary functions, not ordinary just functions. So that's not very scary. It's a strange way to think of ordinary functions, that's for sure. But they're just ordinary functions. So all right. So now we have 0 forms. Great, I guess. So that's nice. I think that's the end of 4.6. Well, it sort of is. Yeah, but I think that really is the end because we did all these things. This is just the same things that we already did. So let's see if we can put some of these things together. I'm again going to pause to make sure I get. All right. A couple more things I want to say here before pushing into the comparisons in 4.7. Some things about uses of each of these. So when we talked about one forms, we first thought about them in terms of force fields. And that worked out just great. The coefficients were just on each of the components. That was our first introduction to all of this by work done by moving by a force moving. The second thing we thought about one forms as was 2D fluid flow. We had one practical example for two forms. That was 3D fluid flow. One thing I didn't tell you about two forms is that we could also think of it in terms of 2D density. This should remind you of something that you did in Calc 3, I think. You probably at some point had some density function xy dx dy. And you integrated it over a two-dimensional surface that way. You might ask what are applications for three forms? Well, again, that would be three-dimensional density. Okay, that seems worth us being reasonable about and not going off too far into crazy math land without remembering that there's physical meaning to things. All right. So there's an interesting comparison here to be made, which is the subject of force 7. There's a comparison to be made between differential forms and vectors. So yes, I'm going to write vectors and put them first. And differential forms. Okay. So for each vector, in R3 at least, if we think in terms of a force field, for example, there's an associated differential form to it, which is a dx plus b dy plus c dz. So we can associate a vector with a one form. We can also associate a vector with an n-1 form, where n is the number of dimensions where the vector lives. We did this where we associated vectors with two forms, because this is what we got when we were doing our three-dimensional fluid flow. We have our three-dimensional velocity vector, and we associate it with a dy dz plus b dz dx plus c dx dy. It's worth noting here the orders we did things in. These are cyclic permutations. Notice we have x component yz, y component zx, and z component xy. If we were to do this in 4 dimensions, if I were to have a 4-dimensional vector, I would have another cyclic permutation that can give me the correct forms there. So that works out nicely. There's something that I've been hinting at that you may have not noticed, and if I have time, I'd like to work out. I'm not sure I do have time though. But I've said a couple times that there are these relations to cross products. The cross product could be computed by taking the two associated one forms. So we have a dx plus b dy plus c dz, and multiplying them together d dx, if you don't mind too many d's together, e dy plus f dz. Multiplying these together using the exterior algebra. No, I don't think I'm going to do that because it is tedious. And then remembering the one, if I have a 2 form, the coefficient on the 2 form, in the first coefficient, the x coefficient belongs with dy dz. So if I were to multiply this all out, I would find that I get the cross product, which is kind of interesting. And that gives us vectors. If I multiply 2 1 forms in R3, I get a 2 form, which associates back to a vector in R3. It's worth thinking a tiny bit. If I took 2 1 forms in R2 and multiplied them out, I would get the product of 2 1 forms is a 2 form, but a 2 form in R2 is just a scalar. Notice it will be in the dx dy component, so it will correspond to that third component. That's the way we've been doing cross products for 2-dimensional vectors. We've just been pretending there's zeros here and then take the z component. So really, in some sense, our fake cross products that we've been doing for 2-dimensional vectors are honest products of 1 forms. That's interesting. There's some very interesting question. What happens if you take 2 1 forms in R4 and multiply them together? That gives you a 2 form. Of course, if you multiply 2 1 forms, you always get a 2 form. But a 2 form in R4 has 6 components. So there's some weirdness where apparently the cross product of 2 vectors in R4 is something with 6 components. Well, that's strange, but okay. The dot product. If you take the product of a 1 form and an n-1 form, then you get the dot product, which is interesting. So let's see how that works out in terms of these, although I will probably change the letters just so that we're not computing the dot product of a vector with itself, which is nice. It's the square of the magnitude, but nonetheless, I will compute now the 1 form. I'm working in R3, so n-1 form is just a 2 form. I have d dx d, no. dy dz plus e dz dx plus f dx dy. And now if I multiply these together, I get a times d, that gives me a dx dy dz. Everything's going to give me dx dy dz, so I'll just put that back there at the end. I get a times d plus dy, that can multiply this one successfully. There's already a dy there, so that will give me 0, and that will give me 0. So I have b times z. Is the order right? dy dz dx. I can switch x twice to get a positive sign. So yeah, that gives me b times e. This is not an accident that all of our differential forms are set up to work out nicely with this. And then dz, don't multiply that, don't multiply that, multiply this one. Cf dz dx dy. I can move the dz back twice. Notice the sign still stays the same. And notice this is the dot product of the 2 original vectors that we have translated into 1 forms and n-1 forms. There's an interesting relationship between the cross product of 2 vectors and the dot product of 2 vectors, which is revealed here. It's also worth noting that scalars can be 0 forms, and scalars can also be k forms. So that's 2 ways to think of scalar functions. All right. In everything we've done so far, with a couple of exceptions when we did with 1 forms, we have only worked with simplices and constant 1 form, constant k forms. Generalizing this, which is what we're doing in our coming work in chapter 8, we will work with generic k-dimensional objects and non-constant k forms. There's a lot of generalization work to do as we build up our stamina for integration. I think probably next time I will have 1 more step of generalization here at the very end of section 4 of chapter 4. And then I will definitely try to get to any suggestions that you guys have for skipping 5, 6, 7. Thank you very much. I'm more tired than you are after having done 2 of these in a row. I hope things are going well, and I hope that I will be back with you soon. Thank you. Bye.